Alright, so we cover section 1.4 on slope fields, also known as direction fields, oftentimes. Alright, so in this section we will describe solutions to differential equations graphically. So up to this point, we have covered one method of solution to a differential equation, that is the method of separation of variables, which is the topic we covered in the previous section. Although we're going to discuss many methods to solve differential equations, unfortunately, not every single differential equation can be solved algebraically or using calculus or, well, in general, analytically. So what we do in this case, well, we look at graphic methods due to the absence of some explicit solution. And also we do this by a graphical approach called direction fields or slope fields. Okay, so to give you an idea of what this is about, so suppose we are asked to sketch the graph of the solution for the initial value problem for the differential equation y prime equals to x plus y with initial condition y of 0 equals to 1. Alright, so up to this point again, if we look at this equation, unfortunately it's not separable. And the reason to that is that we cannot write the right hand side of the equation as a product of a function of x and a function of y. The left hand side, it's fine, that's the derivative term, so that's no problem, but not the right hand side, doesn't satisfy the condition. Well, actually, this equation can be solved using the method we're going to discuss in the next section, that is a linear first order equation, but that's something we're going to discuss later. Alright, well, suppose in this case there's no way to solve this equation with any method. What do we do? Well, so number one, well, first of all, what does that differential equation is telling us? Well, so this differential equation is telling us, number one, okay, let me go about the left hand side of the differential equation, which in this case this describes that the derivative is the slope at a given point. Nothing new. I mean, this is basic calculus, right? On the other hand, the right hand side of the equation describes the structure of the slope, describes how we calculate, how we obtain those slopes. Okay, how do we do that? Well, number one, well, let's explain this. Let me box the right hand side. So in reality, well, because slope equals x plus y, so that means the slopes in the field, in the graph, are going to be, okay, so the slope is defined for this particular equation by the sum of the x and y coordinates of the given point. All right, so that's what this differential equation is telling us. So now but again, keep in mind that when we are solving a differential equation, so again, later we're going to learn how to solve that type of equation. We will be able to describe the slopes at different points, because again, that's what the derivative is. Derivative equals slopes of this form. Okay, so for instance, let's say we want to find a particular solution to the differential equation that contains the point 0, 1. Again, that's what this initial condition means. This means, okay, let me change color here. Okay, so this means when x equals to 0, y equals to 1. Okay, so for your convenience, I have given you the graph of the solution to this equation. I mean, I gave you a completed graph already and a blank. All right, this is a blank direction field or slope field, either way. All right, so this is what we do. I'm going to go to the point 0, 1, that is the point given in the initial condition. That is right here, 0, 1 roughly. It's right here. Okay, so what are we going to do here? You use different color. Okay, same color, red. I'm going to put a point there, and I'm going to try to estimate the curve that best fits within the field. For instance, it seems like the curve can go like this and like that, which is what we have on the graph to the right. All right, so now for instance, what if we wanted to find the solution to the differential equation at the point, say 1, 0 maybe? Okay, let me do 1, 0. That is y. Oh no, let me do 1 of 0 equals to -1. Okay, let me do 0, -1. So for 0, -1, that is going to be this one right here, which happens to be, oh, look at that. Actually, at that point, we have a constant slope. That is, in this case, a negative slope. In this case, this is this slope right here, I mean, or all these points where the slope are exactly equal, is called an isocline. Well, let me actually label that. That's a interesting piece of information. So points where slopes are equal are called isoclines. The prefix iso means same, cline means inclination. So, and again, keep in mind that the slope describes the steepness or the inclination. So, no wonder the word isocline. All right. Now another piece of information that we need to care about. So, the other information, let's say I would like to go to the point 0, 1/2. I believe it's 0, 1/2. All right, so y of 0 equals 1/2. Okay, that's roughly here. Or no, actually I'm not gonna do y 1/2. Let me do 0, 0. Okay, so what happens at 0, 0? So we have another a similar situation. However, see what happens at 0. At 0, we can sketch the solution, but have a look at this graph in this diagonal line in green and this diagonal line in red. In this case, we have the same slope, which in this case it's a negative slope. However, we can see that at every single point, this point, that point, that point, etc., all these points, notice the slope equals to 0, because look at those horizontal lines. The slope of a horizontal line equals to 0, and that the set of all those points has a special name. That's called, okay, so points where slopes are 0, these are called null clines. And in this case, the prefix null means 0, and clines again inclination. So that is all the points where the inclination, where the slope equals to 0. And of course, we can keep sketching many more of this. However, in many cases, trying to do this by hand could be a little tedious, or maybe not tedious, maybe leading to some inaccuracies or lag. So for this, actually, we can use GeoGebra to generate some of these curves. So let me move to GeoGebra, and let me give you an example. So here, that's a GeoGebra project that I'm going to share with you on Canvas, um, and so we can work a little more with this. All right. So we have this blank field for the differential equation, and in this case, I'm going to type the dy dx. Well, dy dx is already given for us, x plus y. All right, we click enter, and well, it's going to generate the same slope field that we had on the nodes, on the graph on the nodes. All right, well, the good thing about this, you can increase the density of the slopes, maybe a little less, make it easier to see, and the length of these slopes, right? Maybe smaller, a little bit, 0.4, it's fine. All right. Now I can drag this point actually, and for instance, I'm gonna look at at, uh, at the point right here. I can drag. I can drag for it. Oh, I did. So in the previous example, what did we do? We did y of 0 equals to 1. Okay. So that means when x equals 0, y equals to 1, which is roughly here. That's the graph we got in red in the previous example. I did also 0, negative 1. That gives us this other curve. What about y? We can move our point anywhere. Maybe y of negative 2 equals to positive 2, and we get this other graph. So many solutions for different solutions for different initial conditions. I'm going to move to the points, to the point 4 comma 0. Y of 4 equals to 0. Okay, maybe the point y of 0 equals to 4. All right, that's another one, very similar to what we did before. And of course, you can fun and play with this slope field calculator, if you will. All right. So that's one example of how direction fields or slope fields work. Let's go back to the notes and look at one more example. All right. Okay, so coming back to the notes, example number 2. Sketch the direction field for the differential equation y prime equals x squared plus y squared minus 1. All right, well, so in this case, I'm going to make a table of values for different points. So for part, okay, I mean, sketching the direction field for the equation, well, actually, let's go to GeoGebra and generate it. All right, so that is, okay, so that's x squared plus y squared minus 1. All right, and that changes the shape of the slope field. Okay, change the slope of the shape of the slope field, mostly vertical slopes, but there's something going on around the center. And again, I'm just going to drag this point so you can see the different solutions we get for different initial conditions. An increasing function, a function that increases and then increases, then decreases, and then increases again. A function that is only increasing. Do I have anything just decreasing? Maybe no, I don't think there's any purely decreasing function. All right, well, let's go back to the notes and do some calculations and then relate to this slope field calculator. All right, back to the notes. Okay, so I'm just going to choose a bunch of random points. Okay, so I don't know, maybe the point, let's see, negative 2, negative 2, 0, negative 1, 0, 0, 0. Actually, that's part B of the problem. They're asking us to sketch the solution curve that passes through the origin, that is that point. Maybe the point 1 comma 0, maybe the point 2 comma 0. What else? Maybe the point negative 1, 0, maybe 0, 1, maybe 1, 1, maybe 2, 1. So I mean, we can keep doing this and more and more and more. I believe I missed 1. Did I? So 1, 2, 1. Oh, I wanted to do. Okay, let me go back to negative 1, 0, negative 1, 1, 0, 1, 1, 1, and 2, 1. Okay, so we're going to fill in the table to find the slopes at these different points. How are we going to calculate the slopes? Well, we have a formula for the slopes because again, y prime, which is the derivative, also equals to slope. Well, this slope happens to contain two variables. We're going to substitute these two quantities right here. Let me show you a calculation here at the top. So at the point negative 2 comma 0, what do we do? Y prime equals the x coordinate quantity squared plus the y coordinate, which is 0, quantity squared, and then minus 1. All right. Well, let's simplify this. Y prime equals negative 2 squared, which is 4, plus 0 minus 1, and that equals to 3. So that means the slope equals to 3 at the point negative 2, 0. Let's go ahead and look at that. So at the point negative 2, 0, does that, okay, that's the slope right here at the point 2, 0. Does that look like a slope equal to 2? Certainly it does, right? It certainly does. Okay, so let me show you another calculation for the next point. Okay, so for the point negative 1 comma 0, I'm going to repeat the calculation. Y prime, okay, y prime equals to negative 1 squared plus 0 squared minus 1. So negative 1 squared, which is 1, plus 0 minus 1, that equals to 0. So at this point the slope is 0. How about we go to the slope field and verify that indeed it is true? Go to the point negative 1, 0. Oh, look at that. Isn't it true? Right? Yes, it's 0. We have a horizontal line right here which represents a tangent because it's derivative. It's a slope field, right? So yes, we can verify that already. All right, well, I'm just going to give you the results of the remaining slopes. I think I already showed you how to compute a couple of them. Okay, so let me just give you the results. So at the point 0, 0, substitute 0 squared plus 0 squared, which is 0 minus 1, that's negative 1. 1 comma 0, that's 1 squared plus 0 squared, that's 1 plus 0 minus 1, that's another 0, and then the remaining numbers 3, 0, 1, 0, 1, 4. All right, okay, so let's go and verify some other points. How about the point 2 comma 1? Okay, so the point 2 comma 1, look at the steepness of the slope. Yes, it looks like a slope of 4, right? That actually helps. Okay, so let's have a look at part B of the problem. Use part A, that is the generation of the table, right? To sketch the solution curve that passes through the point, or that passes through point 0, 0, that is the origin. Okay, so let me just do the dot at the point 0, 0, and well, if we follow the path, it kind of looks like this, like a magnet, you know. And in fact, we have for our convenience, we have a nicer sketch right here. How about we verify this using GeoGebra? Okay, so oh, actually, that's the graph I already had before, with initial condition having y of 0 equals to 0, which is really the origin. Okay, so we can sketch many other solutions. Actually, that's the picture at the very bottom of the page on the handout. All right, so notice we have the graph in red. That's the solution curve containing the origin. How about we generate the curve in yellow using GeoGebra? That is the solution containing the point 0, comma 3. All right. So let's replicate that. Let me drag the point to the point to 0, comma 3. Does that look like the same graph in yellow? Let's compare. And indeed, it certainly looks like. What about the graph in gray? That's at the point. Oh, it's actually not 0, 3. It's 0. It was supposed to be 0, 2. My bad. All right, there we go. Well, it's very similar anyway, but I still wanted to be accurate with this. All right, and one more. The gray one at 0, 1. Okay, that's the graph in gray. It definitely looks very similar. What about the graph in green? What about the graph in green? So, graph in green containing the point 0, -1. Okay, let's go 0, -1. Definitely looks like it. It definitely looks like it. All right. What about the finally the graph in purple here? 0, -2 containing the point 0, -2. That is this graph. All right, now why do we care about this? How are slope fields very, very useful when it comes to solving differential equations? So let's say you're trying to, you're modeling a physical situation or a chemical situation, I don't know, or in engineering, anywhere. So, and you're looking for I don't know, maybe a function that has a particular behavior, or for instance in economics, when it comes to making money, of course, as a businessman you might want to make more money, so that means you want an increasing slope. So solution curves like the yellow one that describes an increasing function, the green one, and then the purple one, those are good solutions to model growth in your economic system, all right? Or increasing velocity or something like that, depending on the situation. However, the red one may not be the best because in terms of an economical situation, we would be looking at some increase or some earnings or some increase, maybe some loss because of the negative slope, and then but at least it's going to increase back again. All right, so depending on what you're modeling, depending on what you desire for a situation like this, well, that's the curve we may want to choose. And what does that depend? It depends on the initial condition that we set. All right, so it's a matter of playing with numbers here and there to obtain different curves, because again, when we solve a differential equation, all we get is the general solution containing the constant of integration, which again, that depicts a family of functions. Now we're having a better picture of the family of functions, because now we have 1, 2, 3, 4, 5 different members of the family having different behaviors, having different shapes. So I think this is a good way to visualize what that constant and what that initial condition is the purpose is for. All right, so that's it for this section, a very short one. So it's a good place to quit.